Hi everyone. Today we're going to start looking at how we would analyze continuity algebraically. So we started yesterday by doing this just with graphs, and today we're going to look at how we do this if we don't have a graph. So actually the first part of this video is going to be a bit of a review from yesterday, but then we'll take this limit definition and start applying it when we only have functions. So if you remember what we learned in the last video, we said a function is continuous at x equals a, and actually, just for our purposes here, I'm going to call it a point C, and you'll see why in a minute. So it's continuous at a point x equals c if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x, which is equal to f of c. So, for example, if I called this point C, we would know that we're continuous at C because the limits from both sides approach the same value, and that value is also the function value. Now, one thing we didn't talk about yesterday is continuity at an endpoint. Now, because this is an endpoint, to show that I'm continuous at that endpoint, all I would have to show is that the limit as x approaches a from the right of f of x is equal to f of a. Since I don't have a piece of the function coming from the left, we don't have to worry about that limit. We only consider from the right, and that would be sufficient to show that I'm continuous at that endpoint. Likewise, if I wanted to talk about b, I would just have to show that the limit as x approaches b from the left of f of x is equal to f of b. And as long as those two conditions held, I would know that I'm continuous at b. Now, last time we also talked about different types of discontinuities and why they kind of failed that limit definition. So the first one we talked about was a jump, and we said this largely occurs with piecewise functions. And the issue here is right at x equals c. Right? It's really easy to see here that the limit as x approaches c from the left of f of x is not equal to the limit as x approaches c from the right. Now, because we failed that limit condition, we don't even need to worry about the actual value of the function because we know already we're not going to be continuous. Now, looking at infinite discontinuities, there's really two cases we could have. Up top here, let's see, it looks like at x equals 2, my limit from both sides is infinity, right? So we do know in this case that the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right. However, because we have that vertical asymptote, the value at 2 is undefined, so we know that's not equal to f of 2, and we fail the test for continuity. Now, the other situation that can occur when we have a vertical asymptote is that actually here, the two-sided limit doesn't even exist. Here I know that the limit as x approaches 1 from the left is not equal to the limit as x approaches 1 from the right. So again, we fail on continuity. The next type was a removable discontinuity that happens when we have holes. Now, what we notice here is our two-sided limit exists. So the limit as x approaches c from the left is equal to the limit as x approaches c from the right, but that is not equal to the function value at c. Now, finally, we have this oscillating discontinuity, and we said this occurs when we have trig functions. And here we have a case, because this is moving up and down so quickly, it's not converging on a value, we actually have the case where the left and right limits are not equal. And that's how we would justify that this function is not continuous at 0. So again, that was a quick recap. Obviously, in all these cases, we had graphs to look at, and where we're really going with this now is if we have a function, being able to determine where the function is and is not continuous. So let's go ahead and turn to the next page. Now, we're going to be checking for continuity. If I'm looking at a rational function, there's a couple things I'm checking for. I'm either checking for an infinite discontinuity. Whoops. Let me write that again. An infinite discontinuity, which could occur if I had a vertical asymptote. Hopefully this isn't too fuzzy. The other situation that could happen is I could have a removable discontinuity, which would happen if I had a hole. So when I see a rational function, those are the two things I'm kind of keeping an eye out for. So when I see this function, the first thing I think of is that I can factor the denominator. So I'm going to go ahead and do that. So right away I notice that those x plus 2's cancel out. So I have a hole at x equals -2. So I'm going to kind of make a note here. I have a removable discontinuity at x equals -2. Now, because this did not cancel, I also have an infinite discontinuity at x equals 2. All right, now with piecewise functions, in this case, there's two types, again, that I'm looking for. The first thing I'm looking out for is a jump discontinuity. And that's going to happen when the pieces of the function don't connect. And we'll see how to analyze that algebraically. The other thing that may happen is I may have a removable discontinuity. So maybe they kind of connect, but at that break point, we don't have a defined value. So here's how this is going to look. If I'm looking at the function f of x, I know my potential issue is going to occur here at 2 because that's the break point for that function. Now, we said that for it to be continuous here, I need to check that the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right, which also has to be equal to f of 2. So I'm kind of setting up an equation that I'm going to test here. So now we need to pull back what we know about limits. If I'm finding the limit as x approaches 2 from the left, I know I care about this piece of the function. And our first rule of limits said to just try and plug 2 in. I know 3 minus 2 is 1, so my limit from the left is 1. Now, from the right-hand side, I care about this piece here. So again, I'm going to plug 2. I get 2 over 2 plus 1, which gives me 2. So I know those two limits are not equal to each other. So I know that I have a jump discontinuity at x equals 2. All right. So the last piece of this then is we're going to look at some functions and we're going to identify the locations of potential discontinuities. So just looking out for things like poles and asymptotes, or maybe jumps in a piecewise function. So first we're going to say, here's where we think we may have a problem. And then we're going to use limits to determine whether or not they're actually continuous or discontinuous at those values. So for example, if I'm looking at number 1, I know I'm going to potentially have a problem. This is a rational function, so I'm going to have a problem wherever that denominator, 2x plus 4, is equal to 0. I know that's equal to 0 when x equals negative 2, so that's going to be a potential discontinuity. So now we're going to go ahead and use our limit definition to test and see if we're actually discontinuous. So if I'm checking for continuity, I need to check the limit as x approaches negative 2 from the left. I need to check the limit as x approaches negative 2 from the right. And I need to check f of negative 2. So let's see how we would do this. For negative 2 from the left, if we think about a number line, here's 0 and negative 1 and negative 2. Something smaller than negative 2 might look like negative 2.1. So I'm going to think about what would happen if I plugged in negative 2.1 into my function. Now, I know that taking this negative number and squaring it is going to give me a positive number in my numerator. If I take negative 2.1 times 2, I get negative 4.2. Plus 4 is going to give me a very small negative number. So if I take a number and I divide it by something very small and negative, that quotient is going to tend towards negative infinity. So my limit as I approach negative 2 from the left is negative infinity. Now, if I look at negative 2 from the right, that might look like, let's say, negative 1.9. So we're going to do the same exercise of plugging it in. So again, on top, that negative number squared is going to give me a positive number. On the bottom, negative 1.9 times 2 is going to give me a negative 3.8, plus 4 is going to give me a small positive number. So now I'm taking a number, dividing it by something very small, so that limit is going to be positive infinity. So right away we see our left-hand and right-hand limits are not equal. We could take a look at the function value. If I try to plug in negative 2, we already know that made the denominator 0, so this is undefined. So in this case, all three pieces are not equal, so we would say f of x is discontinuous at x equals negative 2, and that would be an infinite discontinuity. All right, number 2, here we have a piecewise, and we know that automatically our potential discontinuity is going to happen at that breakpoint. So we need to check when x equals 0. So again, we're going to do our analysis with the three pieces, approaching 0 from the left, 0 from the right, and then we're going to check f of 0. Now, if I approach 0 from the left, I'm looking at my first piece here. If I plug in 0, I get a limit of negative 7 over 2. Checking from the right, if I plug in 0, I get negative 2. And again, right away I see my left and right-hand limits are not equal. So we would say that f of x is discontinuous at x equals 0, and this time it's a jump. Those left and right limits are not equal to each other. All right, lastly, here we have another rational function, and so I'm thinking that x equals negative 3 might be a problem. Now, I also noticed that I could factor the top, so I'm going to go ahead and do this because I'm not sure at this point if I have an infinite discontinuity potentially, or removable. So let's go ahead and factor. We're going to get x minus 4 times x plus 3 in the top. Make sure I did that right. It gives me a negative 12 and the negative x over x plus 3. So I have the opposite of x minus 4. So in this case, we think we're looking at a removable discontinuity. Okay, now we're going to go through our exercise of checking negative 3 from the left, and then the right, and f of negative 3. Now, when we're finding the limit, because we were able to factor, we know we can plug into that simplified equation to find the limit. So if I plug in negative 3, I'm going to get negative 3 minus 4 is a negative 7. If I take the opposite, I get a positive 7. If I'm finding negative 3 from the right, I'm going to do the same thing. So now I know that I have a two-sided limit. So far things look good. However, when I'm finding the function value, to find this, I have to plug it back into my original. I can't use this simplified function. Now, if I try to plug in negative 3, that's going to give me an undefined value. So again, we know now that f of x is discontinuous at x equals negative 3, and in this case, we know it's removable. Everything would be fine if we could plug in this point. I have a two-sided limit, but because I'm undefined here, we have a removable discontinuity. Okay, so that is it for this video. When we come back to class, we'll get a lot of practice working on algebraically determining if a function is continuous. Thanks, and see you back in class.